Okay, here are the solutions to lessons 4 and 5 for this week 2 of quarter 3. The first one, evaluate 8 to the 5/3. So my noticing here right away is that we've got a cubed root here. So we could also write this as 8 to the 5th raised to the 1/3, or we could write this as 8 to the 1/3 raised to the 5th. Either way, we would get 8 to the 5/3. And so I'm going to choose to look at it this way because I know what the cubed root of 8 is. And so I'm going to use that to write 2 to the 5th. And then I know that 2 to the 5th is 32. Problem number 2, it said express or select all expressions that are equal to 64 to the 3/2. So right away, again, I notice that I'm dealing with the square root of 64. So I know that that's 8, so I'm going to keep that in mind. But I could write this as 64 cubed raised to the 1/2 power. I could write this as 64 to the 1/2 raised to the 3rd power. And let's see, I could also, write it as the square root of 64, because that's what 64 to the 1/2 is, cubed. And so I could write this as 8 cubed. So many different ways of expressing 64 to the 3/2. So I notice letter B here has 8 to the 3rd, so I'm going to circle that one. 8 to the 3rd happens to be 512. And then I notice E down here is also a way to express 64 to the 3/2. So I'm going to choose that one as well. And my next problem, number 3, rewrite the expression using radicals. So the denominator is always what root you're taking, so we can say that that's the cubed root of 17 to the 4th, or we could write it as the cubed root of 17 parentheses raised to the 4th. Either way is appropriate. Number 4 is a throwback to Unit 1. So an arithmetic sequence, which means we're adding to get the next term. K starts with 4, 13. Explain how you would calculate the value of the 5,000th term. So I'm going to assume that a sub 1 is 4, and then my common difference, d, is equal to 9, because 4 plus 9 is 13. So this is a linear sequence, and if I think of it as n and a sub n, kind of an XY table, I know that if a is 1, a sub n is 4, and if a is 2, the second term, a of n is 13. So I added 9 here, and so to get the 0th term, I'm going to subtract 9, and so I have a -5 here. So I'm going to start with that, -5, and then I'm just going to add 9 times n each time. So then a of 5,000 would be -5 plus 9 times 5,000 then. But this is, I think, all they were really after is this. Number 5, select all items equivalent to the square root of 24. So letter A says the area of a square with side lengths 24. No, the choice B here is more appropriate. if we're talking about the area of a square, then we would say if the area is equal to 24, the side lengths have to be the square root of 24, because that times itself would give you 24. Let's see, is there any more? The second one also, the positive number x, where x times itself gives you 24, would be another way of expressing the square root of 24. D makes no sense. E, the edge of a cube. Nope, cubes, we're talking square roots, so we're not going to consider anything about a cube. So that's it for that one. Number 6, which expression is equivalent to 23 to the 1/2? That's the same as the square root of 23 from our work last week. Then on to the practice problems from lesson 5, where we deal with negative rational exponents. So we're going to write each expression in the form of a to the b power without using any radicals. So the first one, we've got a square root and a 5 to the 9th. So we could write that as 5 to the 9th to the 1/2 power. And that would be multiplying exponents then. Following our exponent rules, we would have 5 to the 9 halves then. Number 2 there. Now we want to take this and write 32 to the, I skipped b here. So now with the expression in the denominator, something had to be negative here. So let's take a look at that. If we just rewrite it with the 12 to the 1/3 here, that's what the cubed root of 12 is. And then if we want it in this form, though, we don't want it in the denominator, so we're going to shift it up. And anytime you do that, you change the power or the sign on the exponent. So it's 12 to the negative 1/3. And so this next one, I'm looking at this as the 5th roots there. And so I'm going to write it without using radicals or exponents. So let's look at the 5th root of 32. I happen to know, and you will too, that is 2. So let's rewrite this as 1 over 32 to the 2/5 power. Make it positive first. Then we know that that's the same as 1 over the square root of 30, the 5th root of 32, sorry. And we could say that that's squared. And since I know what the 5th root of 32 is, I can write this as 2 squared. And so that very confusing looking expression here is nothing other than 1/4. Number 3, match the equivalent expressions. So from our work last week, the 8 to the 1/3 is the cubed root of 8, which I know is 5. So I'm going to match those, it's 2. So I'm going to match that to letter A. And the negative 1/3 would just be 1 over the cubed root of 8, which would be 1 over 2, or 1/2. So I'm going to match those. And 8 to the negative 1 would just be 1 over 8 to the positive 1. So that's number 1 here. I'll match those two. From last week, the 16 to the 1/2 power is the square root of 16. And so I'm finding that here, 4. And similarly, a negative 1/2 would be 1 over 16 to the positive 1/2, which would be 1 over the square root of 16, which is 1 over 4. And lastly, anything raised to the 0 power is 1. So I choose that to match with F. Number 4, complete the table and use powers of 27 in the top row and radicals or rational numbers in the bottom row. So for the first one, I have 27 to the first power is 27. They've done that one for us. The next one, we have the square root of 27. We want the top row as powers of 27. So we learned last week that that's the same as 27 to the 1/2. And we learned last week also that 27 to the 1/3 can be written as the third root of 27. And to get 1, we know that we must have taken that 27 to the 0 power. And then we go to 27 to the negative 1/2. That would be 1 over the square root of 27. Let's see. Yeah, that's fine. And then the last one, to get 1/3, we must have taken 3 is the cubed root of 27. So we must have taken the third root, and then it would be the negative 1/3 exponent because the 3 is in the denominator. Number 5, what are the solutions to this equation? So this is from last quarter's work. So just quickly, because this is a -2 over there, it's not set to 0, but it needs to be in order for me to find the zeros or the solutions or the x-intercepts. Remember, those all mean the same. So I'm going to have to multiply this out, then bring that -2 over to the left side, and then factor again and find my zeros. So when I multiply these two binomials, I get x squared, and x times 2 is 2x. And then I have to distribute the -1, so that would be minus x, and minus 2 equals -2. So I have x squared plus x. When I combine my x terms over here, I have 2x and minus 1x. So that just gives me a positive 1x. And then minus 2 is equal to -2. And I need to set this equal to 0, so I'm going to add 2 to both sides. So I end up with x squared plus x is equal to 0. So when there isn't that constant term with your quadratic, the best way to factor this or to solve this would be to factor out a common factor in these two terms on the left side. They both have an x, so I would write it as x times x plus 1. These two are equivalent, and now I can say that in order to get 0, either x is equal to 0 or x is equal to -1. So my two solutions to that quadratic would be 0 and -1. And let's see, number 6 then. Let me get rid of this. We want to use exponent rules to explain why 5, the square root of 5 cubed, is equal to the square root of 5 cubed. Just that, however you want to emphasize that. So what we'll do here is rewrite them both using rational exponents. So I can say that the square root of 5 cubed is equal to 5 to the 1/2 cubed, which is equal to 5 to the 3/2. And then I can take that, the other side of this equal sign, and show that I will get the same thing. So I'm going to start with the square root of 5 cubed. And I can write that as 5 cubed to the 1/2 power, which I can write then as 5 to the 3/2. So because I get the same result, I've shown that these two have to be equal to one another. And that's it for this week. I hope this helped. Thanks.